Hello, welcome to this video. Today I'll show you how to perform image analysis for PET-CT data from the Xodus PET-CT. Here I'll show you an image of the scanner. This is a GNEXT PET-CT here, and this is from Xodus, and formerly they were part of SOFI. So I have the DICOMs here in one folder, and they were exported together, the PET and CT data, and you can distinguish them from the size. Here the smaller ones are from the PET, the bigger ones from the CT, and you can just double click one of them and that loads the whole 3D stack in the Imalytics Preclinical software. And here it is, and you can open the 3D view and look at the 4 mice here. So 4 mouse bed, and now you can go back here and drag in the PET data, just one of them, and load it as overlay. That is taking a moment, and then we have both the CT and PET in the Imalytics as underlay and overlay. And in this case, the PET is a 4D image. So when we select it here, we can go through the time, and we have 50 time points. So we can go through the time with the mouse, and you see here a signal in the myocardium, for example. We can also adjust the windowing. Here, make it a bit stronger. And now we can go back and forth in time, and you see how the signal appears in different organs here, like the aorta or vena cava here, and then in the heart or in the kidneys here from the elimination, and eventually it would be in the bladder here, at least in this mouse. And you see some signal in the brain also. And so we can also open other slice views here and slice through and have a look at the data. And here you can see that there is some kind of misalignment. Here you can see it in the heart as well. And so you can use our fusion tool here, this one, and now you can move the PET around. I'll activate the bounding boxes here for the CT and the PET, just to illustrate what's happening. So we're kind of grabbing the PET and moving it around, and you can rotate it. And so let's try to get a better alignment. And let's also have a look at the brain here. So let's try to get the 4 brains into position. Maybe a bit back here. And let's look at the hearts. Maybe change the windowing a bit. You can also use a phantom. Here I'll briefly show that. There are special phantoms to improve the alignment here from Phantech. This is a phantom with lots of spheres inside, and with that you can automatically determine the transform. So this can help fix the alignment issue, and then you can save the transformation and load it here with the fusion menu. So this is a way to correct the image alignment, and then you can apply it to other datasets. And then as a next step, you might want to crop out the mice. And here this mousepad actually has an interesting phenomenon. It has ribbons on the side here, see here, this is one ribbon here, 2 ribbons, 3 ribbons, and 4 ribbons, and that indicates the mouse position or the ID. So this is mouse 1, so we can go here, and now we can use the cropping tool to crop out this mouse here. So we now have cropped both the CT and the PET, and you can later, if you're not sure if you have the right mouse, you can always check, and you can see the ribbon here. And so now this is the dataset of one mouse cropped. You can also look at the properties of the dataset here with the show image information dialog, and here you see the voxel size of the CT, 200 micron isotropic, and here for the PET we have 50 time points and around 0.5 millimeter voxel size. And what's interesting also here, the PET, the unit is becquerel per ml, and that was loaded with metadata. And now you can check the metadata and see if everything is there here, and this is actually not the case. Some parts are missing, so the injection dose for this mouse, so you can enter this if you know it. You can set the time point here. I don't know what it was, but it usually is a bit before the scan, maybe 15 minutes. I'm just making it up here, and the mouse weight, I don't know what that is either. I'm just gonna enter 23 gram. Now you can set the metadata and close this dialog. And now you have adjusted the image, both the underlay and overlay, from the cropping and setting the metadata. Now you can save them here, save underlay as, and let's just save it to the desktop. Here is the Xodus, and this is mouse 1, and here we can save it as CT, the underlay, and we can save the overlay as PET. And now we can click undo a few times until we have the 4 mouse thing again, and now we can crop out the next mouse here, this one, and do the same thing. Go to nuclear SUV calibration, enter the injection information, time point here from the injection measurement, and the weight, 19 gram for example, and now we can save that as well here in the folder next to this one here, M2, CT and PET. And now that since we have the metadata, we can also convert to SUV here with this dialog. And now we have everything. You can just click apply, and now you might need to adjust the windowing here. And now the unit was changed to SUV, and you can save this image as well. Here, call it SUV, and then you can click undo, and the unit is back in a becquerel per ml, and you can also convert it to %ID per ml, which is another conversion also frequently used in nuclear imaging. And you can save that as well here as %ID, for example. Now I'm going to hide the bounding boxes again. And now typically you want to do some analysis, some organ segmentation. So let's go to the heart, for example, here, and add a class of heart. And we can use the ISO tool, for example, to segment the heart here with one click. And now we have a region, and we can go to the kidneys here, add a class kidney like this, and this maybe, oh, that was maybe a bit too much. And so this is it uses the point where you clicked as seed point and the intensity where you clicked as a threshold, and is performing a region growing operation. Now you can compute the statistics here, and you have a big table with information here. So we have 50 rows for the heart with the different mean values in the PET image. And if we scroll down, we have it here for the kidney, and we have the curve here, the time activity curve. So I think this looks like as if the scan started a bit before the injection, and so maybe there was a catheter placed. This tracer, by the way, was FDG, and it was a scan that took around, if you go to the last time point, yeah, around 1 hour or maybe a bit longer. Yeah, so there are many other ways to segment regions. So you can do a thresholding here for the lung. You can here with the info mouse button, you can look at the intensity, then add a temp class and perform a thresholding, everything below maybe 200 Hounsfield units. Make sure you're in the underlay here, and then you can add a class lung and fetch it here with this tool, then delete the temp class, and you have the lung. Here you can look at it. We have a nice transparent rendering, by the way, and you can cut away the trachea here using this tool to remove the trachea from the lung. And you can perform a morphologic closing operation to fill the holes in the lung. Let's try one more organ, see if we find the bladder. For example, I think it's this one here. Zoom in and use the scribble tool and just delineate it in a few slices, and then connect it using this button and go through, and you can add some more annotations where it is not good enough yet, and then add the class bladder. It is selected as output class, and then you can accept the scribble tool, and now you have the bladder here segmented. And now if we look at the statistics, we have 4 curves because we have 4 organs. And now that we have performed the segmentation, you can also save the segmentation as a file, or you can also save a project file here for project. And now you can close the software, and let's go to here, mouse 2. Here we have the project, so you can open it again later, and you get back to where you stopped, and you can look at your rendering and adjust it, and or go to a different slice. And when you're done, you can save the project again and close the software. Okay, I hope this helps. Thank you. Bye bye.